And there's this handout. And, well, I guess I won't. If somebody's watching on Zoom or later, it's the last problem about lifting a satellite. Oh, there is one other thing. Okay, there's one other thing that Kemp and Offstars that I've been meaning to say, and I forgot to say, which is if you look at the assignment, I think this only comes up in the physics, the work problems, but if you look at actually all of these, it's like 15, 17, yeah, 15, 17, 21, and 23, I think are the problems. One thing I want to mention is that in British units, weight and mass are conflated with each other, right? Like in whatever they're called, international units, whatever the standard units, like a kilogram is mass. Something that's a kilogram on Earth will also be a kilogram on the moon, because it's the amount of something that you have. But if you want like the force of gravity on that object, you'd have to multiply by 9.8 on the Earth, and you multiply by a smaller number on the moon. You know what the moon's grav G is on the moon? I don't remember. You don't have this at instant recall? What is actually I want to force of gravity on the moon. I'm curious. I think it's like 30% gravity or something. Oh, it's 1.62. Wow. 9.8 on Earth, 1.62 on the moon. So it's a lot less. So when you're using units of kilograms, you have to multiply by gravity to get force weight, right? But when you're using British units like pounds, that already is weight. And something that's 100 pounds on Earth will only be like 20 pounds on the moon, right? So the gravity is already baked into that. So you don't, there's the number, I think 32.2 feet per second squared is gravity in British units. But you don't have to multiply by gravity. So maybe I'll just write that down quickly. So that's just one thing just to notice is that like, as soon as you have something as terms of a weight in terms of pounds, it's already like the force. Because its weight is like a force, it's like a downward force. So yeah, so in international units, metric, is it metric? I guess it's metric. I don't know what it's called. It's mass equals kilograms, mass in kilograms. To get weight, to get gravitational force, or slash, it says this in the book, but I just want to make it clear. You multiply by, kilograms by 9.8 meters per second squared. And then the force unit is newtons. Newtons, which is kilogram meters per second squared. But in English units or whatever it's called, pretty outdated now, but we still use them a lot. This book uses a bunch of them. In English units, mass and weight are conflated, are both in pounds. So the gravity is already baked in, meaning you don't need to multiply. Don't multiply by G. I think it's 32.2 feet per second squared in these units, right? Here, this is G. Okay, so don't. And then the force unit is like foot-pounds. It's like pounds is like the force. I'm sorry, not the force unit. The force unit is pounds. And the energy, I guess energy up here is joules, which is Newton meters, right? Force times distance. But here the force unit is just pounds. And the energy unit is this stupid foot-pounds. So everything in terms of that is in terms of foot-pounds. So those are your answers for like your energy. So it's kind of silly. And if, I mean, I guess I could have just changed all the measurements to, where'd that go? Yeah, but if you look at the problems on the homework, they're actually all in terms of pounds and feet. Most of the problems in this section are in terms of feet and pounds. So they actually give you the, so you don't need to multiply by gravity at any point. And they give you the density of water. Actually, it's funny, you need the density of water. We realized in offstars today, you need the density of water in 17, 21, and 23, but they only tell you the density of water in 21 and 23. So I don't know why they don't tell it to you in 17, because you need it in 17 also. So it's, I guess in this units, it's 62.4 pounds per cubic feet. Cubic foot of water weighs 62.4 pounds. That seems like a lot. But okay, does that make sense? So just don't multiply. Okay, I just want to say that because it's a confusing point and it's a little bit annoying and I'm going to be gone. So, okay, work. Let's do this work problem. One more work problem. The last one on the handout, the physical integrals handout. Yeah, it's this one. So the problem that when we were pumping the water out of the tank, remember there the idea was that you certainly slice vertically, but each slice is some slice of the water, and then each slice is being lifted a different distance. So force times distance. The distance is what's changing. The force is changing in that it's a different amount of water, but the distance is also different because each slice is raised a different distance. But in this problem with like the satellite, trying to raise a satellite from the surface of the Earth up to 2,000 kilometer orbit, well, there's only one object. You think of it almost like a point. Like 1,000 kilograms is just a point mass. And you're lifting that. So it's actually what's changing is the slices are the slices of distance that you're passing through, bless you, because the force changes, right? So let me just write this down. So work required to lift 1,000 kilogram satellite from surface of the Earth, which is actually the radius of it is 6,400 kilometers. So from height, see, it's really the height really from the center of the Earth is 6,400 kilometers, which is 6.4 million meters, right? So this is 6.4 times 10 cubed kilometers, which is 6.4 times 10 to the 6th meters, right? You multiply by 1,000, you multiply by 10 cubed to go from kilometers to meters. To height 8,400 because it's going up 2,000. This is the surface. This is the surface of the Earth. We have to measure everything from the surface of the Earth. I mean, we should be measuring everything from the center of the Earth. We're talking about gravity, right? So that's 8.4 times 10 to the 6th meters. Okay. And let's think about what gravity says. Gravity, well, it's 9.8 to the surface of the Earth, but it's not 9.8 everywhere, right? Gravity is, well, the force of gravity. It's Newton's law, right? It's like you guys remember this, Newton's law of gravitation. You have the two masses of the bodies. You multiply, you divide by the distance between them, and you have this constant G, capital G, which is something. But I think the point is like, if this guy is the mass of the satellite, and then this one is the mass of the big M is the mass of the Earth. And so if these are constants in this problem. I mean, M, I guess the mass of the side is constant too, but so G times M is some number which apparently is 4 times 10 to the 14th, something, right? So it turns out that if you want to just do some object with regards to the Earth, you combine G and M into one constant, and it turns out to be, what did I just say, 4 times 10 to the 14th. I have to think about the units also. Times M over R squared, where R squared is the distance from the center of the Earth. That's why we're using the center of the Earth. Okay. Does that make sense? What are the units here? I guess this must be in kilograms. No, is that right? No, this is mass. This is in kilograms. Oh no, this is a weird. It says kilograms per meter squared. So this is some very strange unit that makes everything cancel and turn this into newtons. So I'm not even gonna worry. It's not so important. This is in newtons. So okay. So that's gravity. That's how gravity works here. So let's draw this. So, because I'm always in these problems in drawing an axis, right? So this is R. This is 0, the center of the Earth. And this is 6,400 kilometers. And we want to raise it to 8,400 kilometers. This is not to scale, but and so this is what we want to raise from here to, from here up to here, right? But what changes, so each little patch of distance you pass through is going to have a different force associated to it, right? So it's more like what we have here is we have like a dr. I almost want to make this even more ridiculous, like just so we can see it better. I'm just going to make the Earth pretty small in relationship to. So here's the Earth. Here's 6,400 kilometers. So this is definitely not to scale because that's 2,000 kilometers, not 6,400 kilometers. But we want to raise our satellite from here to here. And we have a little dr here, which is a little bit of the distance, a tiny piece of the distance traveled by the satellite, right? By the satellite. And what we want to do is we want to multiply, we want to do force times distance. So it's like we're going to sum the work, the little bits of work, but again, in the pool, it was each slice of water was the full amount of work it was doing being raised up. here we have our sort of point mass, and we want to measure the work done over each little interval and then add up all those. Does that make sense? Or I can look like you had your hand up for a second. No. Okay. Okay, so the work done, let's see what the work done over this interval. Interval. Well, it's force times distance. So the point is on a little tiny interval, we can consider the force to be constant, right? That's what we're doing. It's like we're just saying, if I'm only changing my height by like a meter out of this whole 2,000 kilometers, then I can just assume the force is some constant over that meter, right? Like we still say the force of gravity is 9.8 here and 20 meters higher, even though it might be slightly different, you know, at the like 10th decimal place, it might be different or something. So it's the force of gravity at this height times dr, the distance traveled. Right, because work is always force times distance. Does that make sense? But we know the force of gravity at this height. It's given by exactly that equation up there, right? And m here, little m here is 1,000 kilograms, right? So this, yeah, like this is dr. This is, I'm forgetting this number, 4 times 10 to the 14th times m over r squared, but m is 1,000 kilograms. So that adds another 3 zeros to this. So then that makes it 10 to the 17th. You multiply by 1,000. So that's 4 times 10 to the 17th over r squared. Okay. And so the work is just this number times dr. The force of gravity times the distance over to travel. So that's, yeah. So work, I guess the little slice of the work done is 4 times 10 to the 17th over r squared dr. Okay. So the total work is going to just be the integral over all slices of work. Just add up the slices. Sum up slices of work. And we can always do these as Riemann sums, but I tend to like to jump straight to the integral. And so this is an integral of this function. What are the boundaries of the integral? What are the bounds of the integral? Where do we start? Where do we end up? Yeah, exactly. It's 6,400 kilometers to 8,400 kilometers. Although probably this is all should be in terms of meters. So I should do the 6.4 times 10 to the 6. There's going to be a lot of powers of 10 floating around here. This is fun, right? So they actually end up with an integral that's not hard. It's just the numbers that are unpleasant. Yeah. Okay.
Radius of the Earth plus 3.
Oh, the radius of the Earth is 6.4.
Oh.
That is the radius of the Earth. Yeah.
Okay.
Yeah, sorry. The radius, yeah, the surface of the Earth is at height 6,400 kilometers because 0 is the center of the Earth. So the surface is 6,400. Yeah, we're measuring everything from the center of the Earth. I guess, did you know off the top of your head that the radius of the Earth was 6,400 kilometers? No? Did you? No. Wait, what's the circumference of it? It's 2 pi r. I thought the circumference of this was about 20 thousand miles or something, 24,000 miles or something. Is that the same thing as 2 pi times 6,400 in terms of kilometers? 36,000 kilometers, 24,000 miles, something like that. Okay, anyways, I don't know. Okay, so let's just do this and see what we get, just because this is not hard now. This is the integral we have to do, but it's just integrating r to the -2 power, which is not bad. But let's just see, I'm kind of curious how this works out. So I'm going to pull this constant out. And it's basically when we integrate 1 over r squared, we get -1 over r from 6.4 times 10 to the 6th to 8.4 times 10 to the 6th. Oh my God, what's going to happen here? How do I want to do this? I mean, lots of times I just say, I really care about the setup more than the answer. Right, but this I'm just sort of curious now, like what kind of number we get in terms of, the answer should be joules. And we were talking in office hours about the answers you guys are getting in, but they were just weird numbers, like huge numbers, and it's hard to get a sense of what it even means. But okay, so this is 4 times, let's see if we get a positive number, because that's the first thing. -1 over 8.4 times 10 to the 6th minus -1 over 6.4 times 10 to the 6th. Are we going to end up with a positive number? You argued. This fraction has a positive sign, this fraction has a negative sign. But the denominator here is bigger. So we're subtracting a smaller number from a larger number. So yeah, I think it's going to be positive, which is good. Sometimes when these minus sign shows up, you get worried. I could factor out a 1 over 10 to the 6th from this expression. Again, it's not the most important part, but it's kind of fun to see. This is my definition of fun. I don't know about you all. So 4 times 10 to the 17th times 10 to the -6th times 1 over 6.4 minus 1 over 8.4. That's 4 times 10 to the 11th. I mean, I don't know how we want to do this. You could do this explicitly if you wanted to. You could ask a calculator. You want to just ask a calculator? It's sort of sad. Google search bar is a calculator. I'm tempted to turn this into 10 over 64 minus 10 over 84, factor another 10, and do 1 over 64 minus 1 over 84 explicitly, which is 20 over 84 times 64. Oh, let's do that. Okay. I know you want to do this. Calculators are for the weak. Factor out of 10, 4 times 10 to the 12th, 1 over 64 minus 1 over 84. 4 times 10 to the 12th, 84 minus 64 over 84 times 64. Right, so how we subtract fractions. This is 20 over 84 times 64. You guys are looking at me like, what are you doing? Why are you doing this to yourself? Okay, 4 times 10 to the 12th times 20 times 1 over 84 times 64. 28, this is 8 times 10 to the 13th. I split this up into 2 times 10. I can put the 2 with this. I can put the 10 with that. 84 times 64. It's got to be close to 5,000. It's 74 squared minus 10 squared. 74 plus 10 times 74 minus 10. What's 74 squared? Anybody know 74 squared off the top of their head? No, it's probably 50, can't, almost had it. I'm gonna get it. 74 squared. 4,900 plus 5,600. No, that's not right. 4,900 plus 560 plus 16. It would be long. It would be less time to just multiply it out, right? $53.76. Okay, that's about 1 over 5,000. Let's just say that. Takes off 3 zeros. So 8 over 5 is 1.6 times 10 to the 10th. I don't know why I did all this. I have to entertain myself somehow. This is 16 billion joules. It's about 16 billion joules. That seems like a lot. That's why space travel is hard. If you're going to work for NASA one day, you're all going to work for NASA one day, right? You need to be able to do this. You're going to work for NASA one day. So let's just say it. Okay. Anyways, I don't know. I really don't know why I did all that. Okay. I think my brain is halfway on break already. Okay. So, and I said this is fun for me. So, okay. The point of that was just the setup, right? And then you can do all the rest. Ask a computer, a calculator to do most of the rest. But I do like to somehow mess with the powers of 10 and see what basically the order of magnitude of the answer is going to be. So I think that's 16 billion, 1.6 times 10 to the 10th. 9 zeros is a billion, right? So that's 16 times 10 to the 9th. Yeah. Okay. I still don't know what a joule is, so I don't have a sense of how to estimate. But a billion seems like a lot of something. Okay. Actually, let's take our break now a little early, and then we'll come back and do the. I want to start with the probability and statistics stuff and just start talking about it. But it's going to be kind of weird because we're not going to have class till next Wednesday. So let's take a break for a few minutes and then spend the rest of the class talking about getting into the probability stuff. Yeah. Woo, fun. I'm going to ask, see if we were even remotely correct. Seven times 4 times 10 to the 11th. Okay, so that's 1.48. So the actual answer is about 1.48 times 10 to the 10th. There's your actual answer. is what we'll start talking about next. It's funny, I have handouts for this stuff and I have videos for other stuff. Once we get to sequences and series, we'll be back to a lot of videos. But I just somehow wrote a handout for this. So. Big fall break plans besides binging Squid Game? New York City? Oh, that's home for you. That's right. Yeah. That sounds good. Blue Hill? Blue Hill, Maine? How many people are in the New York area now? Is it like 17 million? Tokyo is still number one, 37 million. But I saw like some demographic predictions that like by the middle of the century, Lagos, Nigeria will have like 50 million people and will be the number one most populated city in the world.
Well, Africa's growing faster than any other continent recently. So they're predicted to have the largest population of any.
Yeah.
50 years. But that's also because the current statistics aren't sustainable in a modern society. Because on average, the average family has like 6 kids, I think, you know?
Ooh.
And that's just not sustainable when you get into more modern society.
Wait, the average family across the world has?
No,
Oh,
in
Africa.
in Africa.
Oh, okay. Well, yeah, that's right. Like Tokyo will shrink actually over the next 50 years, and like a lot of China, probably a lot of the population will also go down.
The Tokyo thing it's not. They're a really big area, right? Because it's not just like the city; it's like the metropolitan area is 37.
Yeah, but it's kind of crazy that you take the high-speed train out of Tokyo, and like an hour later, you're still in Tokyo. So it does go. It spreads quite far. Okay. Little breaky break. But this is the last major unit before we start sequences in the series. So we'll start this today and finish it Wednesday and start sequences in series probably the Monday after break. So that will be occupy a big chunk of the rest of the semester. So, all right, I wrote this handout. There's these sections, there's 2 sections in the book, the last 2 sections of chapter 8, talk about all this stuff, but I just tried to distill it down into some kind of manageable handout. So we're gonna talk through some of this, and then there's some problems we can do together, or you can do it maybe just at your seats, like as we talk through this stuff. But what I really want to talk about is the idea of a probability distribution, which is kind of a strange concept. Oh yeah, I'm sharing screen, good, okay. The idea of a probability distribution is kind of strange. And I want to show how we can build it kind of naturally, like an example kind of naturally, so that we can see what like a probability distribution actually is. So, and this idea of a probability density function. So, okay, so like here's a set of data of, I guess this is from 2012. So fraction of population in different age ranges, right? So 27% of the population is between 0 and 20, 27%, 28%, and then it goes down, right? Only 3% of the population is above 80, 15% of the population is between 60 and 80. And you can make a histogram of that, right? Like you can make just a box, like boxes. Like from 0 to 20, I want to make a box that's area 0.27. And from 20 to 40, 0.27. And from 60 to 80, I want a box whose area is 0.15. 80 to 100, a box whose area is 0.03. So that when you're talking about probabilities, everything's supposed to add up to 1, right? And if you want to relate probabilities to area, you want the total area to be 1. And so this picture, this diagram is kind of manufactured, contrived in a way to make the total area underneath within all the boxes equal to 1. But then the trade-off you get for that is that all of a sudden the y-axis becomes a very strange concept. Like here, since this is about age, you know, the horizontal axis is very natural, it's just age. But then because we're using, I mean, the boxes are sort of dimensionless. The area is sort of a dimensionless number, right? It's just, it doesn't have units. It's just 0.27, you know, the area of this box is just 0.27. And so then all of a sudden, if the base is age and the area has no units, then the height needs to be like 1 over age or something like that to have the units cancel out. Does that make sense? Like you want the units to sort of cancel, so it's like 1 over age. So, but I mean, if we want to say that a little more like conceptually, you can think of this as the fraction of the population per year of age. So it's a little bit strange, but like one thing you could do is you could imagine breaking this up into 20 tall, thin rectangles, so that for each year, you would have a rectangle for that year. And assuming, I mean, it's a big assumption, but assuming the population within each 20 years was distributed evenly, you could figure out how many people are, like what percentage of people are between like 7 and 8 years old. Because it would be that area divided by 20, I guess. But then the height of that box would actually be that percentage of area now. If the base was 1, if we made a rectangle whose base was 1, then the height really would be the percentage. So that's why the y-axis is kind of strange in probability distribution functions. It's like, it's this kind of manufactured thing just to make the area underneath 1. Okay, so, all right, I guess I write this down somewhere, like this explanatory paragraph right here. Not number of people in that age or even fraction of people, but fraction of people per year of age. Yeah, I guess this is just recapitulating what I just said. Yeah, it's a little hard to say that like the first box has height 0.0135, which is kind of just a strange number to think about. But then what you start doing is this is a pretty coarse measurement by just breaking up the population into 20 years, chunks of 20 years. But you could do 10 years and get something slightly more sophisticated. It's like something slightly more sophisticated, right? You could do every year. You could just say how many people are each age. And you would get a lot of thin rectangles, which starts to feel Riemann summish. And then you get kind of a graph along the top. I mean, this is what this is doing. It's smoothing out, smoothing out the age histogram. So like, this is 10 years, but you can sort of try to draw a smooth curve that sort of follows the top of the boxes. And especially if you had more thin box, if you broke it down, I mean, you could give everyone their age up to the day, and then you could sort people by age up to the day, and you'd have a lot of really thin rectangles. Everybody who's like 15 years, 1 month, and 7 days old, you know. And then you get all these little like thin rectangles, and then the top would be more like a smooth curve. Does that seem fair? The more rectangles you have, the top would look more and more like a smooth curve. And that curve is the probability distribution function for this data set. So like if you could break it down more and more, but what we do is there's actually these smoothing techniques people use to like, because you don't usually have it broken down that finely, the data that finely. So there's ways to use smoothing to like make the function. And that function is called the probability distribution function. But let me get to that. I'll get to that and I'll write some stuff down. So yeah, more and more bends representing narrower and narrower edges. Bends to the top there to smooth out. Okay. This function is called a probability density function. People call them PDFs. It's not portable document format. Is that what PDF stands for? Portable document format? Hey, you learned something in math class today. I think it's portable document format. So it's not that PDF, it's this PDF. Yeah, probability density function. So like I'm saying in that next line, the values of a PDF don't mean much by themselves. In fact, the thing you really want to look at is something like this. P of t times delta t, because that's a rectangle. And that tells you about the fraction. The area of that rectangle is about the fraction of the population that fits that data, that little piece of data. Okay, so maybe I'll try to write some of this down. So probability density functions. PDF, PDFs. So given a data set, we can plot sort of as, I mean, it's sort of hard to say it in words, but it's like we're sort of plotting like you have to sort of think what the data set is, right? So there's like the data is actually, in this case, it's ages, it's age range. It's like the age of people. You can do it with heights, you could do it with anything, right? Heights, you would see more of a like bell curve because there's people who are really tall and people who are really short, but they're less common, and more people in the middle. So you could plot heights within like millimeters of each other and then like get a nice smooth curve. Or again, you could get boxes and then like kind of smooth it out. So we can plot histograms, which are just those boxes, i.e. boxes representing the data that add up to where the total area underneath is 1. So yeah, so like here's your data. It's some numerical data, I guess. This isn't like Republican, Democrat data. This isn't like something binary. It's something that actually is like a number. Not that that's binary. Anyways, let's not go into politics. So you have like, yeah, you have something, you know, I can imagine with heights, it would look more like this or something, right? You'd have these distribution of heights more like that or something. And yeah, the total area underneath is 1. Yeah, total area equals 1. And the top of this is the PDF function. Yeah, we can sort of draw histograms, and then sort of the top of the boxes forms our function, forms our PDF, but usually smoothed out or modeled somehow. I'll show you, we're going to model the age data just down there. So the problem is that the axis is fraction of data per unit of data, which is just such a weird concept. Data per unit of data. That's kind of the abstract version of what we just saw with the ages, right? And then we call this P of T. I don't know why T of T is the variable. It could be, well, whatever. So usually smoothed out. And then, like I said, P of T itself, did I stop the share? I never stop the share. Please share the share when I should. Okay. So P of T itself doesn't mean a lot. Doesn't have an easy meaning, have an easy natural meaning. It's just a weird thing. So we're used to functions having meanings, you know, like functions and applications, we're used to those having meanings. But here it's more like P of T d delta T. But P of T times delta T represents the fraction of the data between T and T plus delta T. Right, you just give yourself like a range. like delta t is almost like picking a range of the data you want to look at. And then go from t to t plus delta t. Does that make some sense? Okay. Now if we go back to the picture, back to the screen. So you could make, this is what people do, is like you try to make a function that'll work for your data set, and that's your PDF. And this is sort of modeling. You're like modeling, you're trying to pick a function that like, you're trying to make a function that fits the data, the top of the boxes. And so here's a crude one that we could do. And then we could sort of use this to find the number, estimate the number of people between like age 35 and 43 or something like that, right? If you have this model, then you could sort of start estimating different age ranges besides just what the data gives you. So the top of most of those boxes was 0.013, up to the point where the age starts to come into play and people start dying off. And so we had something that was like boxes and then it kind of tailed down, but you could just move a straight line and a straight line down like that, right? Like a horizontal line and then an angled line. Okay, and so what I want to do though is I want to find, like if we do this, we want to give this function like from 0 to 60, it's just constant, it's 0.013. But then from 60 to whatever, it's this negatively sloped line, right? And so we're going to want to find the equation of that line eventually, but we need to find what b is, like where this line hits the horizontal axis. And what we need to do that is that we need the total area underneath to be 1. Right? We need this total area under this weird trapezoid thing to be 1. And if that area is going to be 1, then this is going to determine what b is. So maybe you guys can start answering these first couple questions here. Like, I don't know, we don't have to go fully into groups, but you can like turn and say hi to someone near you. Hi, turn and say hi. And then see if you can figure out, like based on the information given, like what b has to be to make the total area 1. Does that make sense what I'm asking you to do? Find b. I claim you have enough information knowing that the total area is 1. Yeah, so see if you can work on these problems. You don't have to be that crazy. You just need area, just areas of triangles and rectangles. Yeah. Oh, okay. Yeah, it's horizontal from 0 to 60. And then at 60, it starts going down and it hits the axis at 60 plus b. Yeah, you're right. This is a good point. You should think that there's kind of a vertical line from this point down to here, and that's 60. Right, so this is really, you could break this up into a rectangle and a triangle, basically. So you should be able to figure out what b is. Start drawing this picture on the board so that we can do it together.
1 minus this function. So if you write 1 minus
We're finding B. You might have to do, plug things into a calculator or something. If you found B, you can try to answer questions 2 and 3 also. Oh, I'm going to a family memorial like thing. Yeah. No, that's okay. That's fine. I didn't really say what I was going to. Yeah, no. Things are still very virtual conference wise. So.
No, so
Yeah.
you have 1 minus
No, it's big party time at math conferences, let me tell you. People find it? Nobody's actually writing things down, they're just talking it out. Is that what people are doing? Like the rectangle plus the triangle? Did people solve for B? What did you get? 33.846. Well, I think in the picture B is just that width. It's just how we're labeling things. You're right. If we want to find the actual X coordinate here, we need to either add 60 or call the whole thing B. Yeah. Sorry. So what did you say? B was 33, approximately 33 point what? 846. Okay. So that's B, which means question 2, we've killed off everyone over a certain age. What age do we kill everyone off over? 93.846. My grandmother's turning 95 this month, so she's dead. Sorry. You guys killed my grandmother. It was you. Okay. So yeah, so that's so right. So then actually this is basically 93.846 is there, whether we get down to 0. And so we're just kind of assuming there's nobody older than that. That just is a rough model, right? Clearly it's not correct, but and notice there, the third one I wrote, you can actually write down P of T like completely explicitly if you want to. Sometimes it's good to do that. So let's try to do that. So that's what this you might not have seen this kind of thing before, but it's called a piecewise defined function. And it's kind of silly that we're saying from -infinity to 0 and from, I guess, 93.846 0.8 to infinity, the function 0. But it's sometimes nice to just think of this as like something that's defined everywhere. So basically we need the equation of this line, right? So what's the equation of this line? That's some good point slope. Or what's the slope of the line? It's rise over run. I guess the rise is negative 0.013. Over the run is this 33.846. So because, I mean, this is not drawn to scale, right? This number is very, very tiny. Like the actual graph drawn to scale, we wouldn't be able to distinguish it from the x-axis. So this is actually a very small slope. What does that end up being? Let me ask. 3.846. Am I doing this right though? 0.00003. I'm tempted to use powers of 10 again, but let's 0.000384. Okay, so that's negative is the slope. What's this point? This point has coordinates 60, 0.013. Right? Do you remember your point slope? The equation of the line through that point? Familiar? Basically, slope is changed in y, we're changing x. That's the worst one? Yeah. Yeah, but you don't always have the y-intercept. So, and this is conceptual. It's basically, this is delta y, that's delta x. So the slope is delta y over delta x. Okay, so y minus 0.013 is negative 0.000384 times x minus 60. This is fun. So you could simplify this and get the actual function, the actual equation of P between 60 and 93.3. Oh, let's see. Let's multiply this times 60 because we're going to end up multiplying those two numbers together. And then add 0.013. Wait, this is a net. Oh no, that's a positive number because it's a minus times a minus, right? Multiply this out, we're going to get this negative times this negative, which is apparently 0.023. We're going to add 0.013, which I think is 0.036, 23 plus 13. Yeah, 0.036. So this is y equals negative 0.000384x plus 0.036. So that is the equation, and I really should be using t probably instead of x. T. Okay, so our function, this is called a piecewise defined function, where you give different formulas for different intervals. And it's often written this way, like it is on the screen down here. So it's 0 for values less than 0 because the data doesn't make sense. It's 0.013 for t between 0 and 60. I guess there's like a less than or equal to here probably. And it's this equation. That's for t between 60 and 93.846. And it's 0 for 93.846 less than t less than infinity. Is that right? That's kind of the, yeah, those are the numbers we filled in the unknowns on the screen, right? So that is your probability distribution function for this data set, or this model of this data set. Okay, fair enough. Fun, right? Okay, maybe. Let me talk a little bit about, there's some just properties that are nice to know. So these properties are helpful. So it's a little bigger. Let me share screen again. I mean, I'll probably write them down and make you write them down. But yeah, if you have a general PDF, P of X, think about what has to be true. It represents some probabilities, so some fractions of data. So datas always have to be non-negative. I mean, probabilities are non-negative. Not sure what negative probability would be. Probability of you getting an A in this class is negative 1,000,000. No. It's fun to say, but it's meaningless. Okay, so all right, so people read, oh, sorry, am I cutting off the board? It's so weird these boards are recessed. And students can't see when I write. Sorry, Thomas. Okay, so then, yeah, so these properties, if you just read them, so like, so the property 2 is a little bit silly because it's just like in general, we don't know when the data is going to start and end. So we tend to just say from negative infinity to infinity. The integral should be 1, meaning the data under the PDF curve. The area under the PDF curve should be 1, right? Because it's all the the possibility of something happening is 1. Right, so all the probability should add up to 1. So properties. First one is that, right, greater than or equal to 0 always. 2 is that the area under the whole thing should be 1. And 3 is that if we take the integral from A to B, this should be the fraction of the data between A and B, right? The probability of like that some randomly chosen piece of the data is between A and B. Equals the fraction data between A and B. Right? That's what that's supposed to represent. Okay. Well, those make sense conceptually. All right, so let's ask like one of these questions at the bottom of the screen now, like what's the, like maybe part C there. Like the percentage of the population between 55 and 60, according to the model that we have now, what percentage of the population is between 55 and 65? According to the age data model, what percentage of the population is between 55 and 65? Okay, well, how can I write that as just a very abstract expression? Yeah. Good. Yeah. So the fraction is the integral from 55 to 65. That's exactly kind of what this third one says, right? We have, I guess it's written in terms of T, so. But now this is a little weird because it's a different formula for to the left of 60 and to the right of 60. Right? So if we're actually going to evaluate this, we'd have to break it up into 55 to 60 plus 60 to 65. Because the formula changes. Because of the piecewise defined nature. Okay, so if we did that, we'd have 55 to 60 of just this constant, right? 0.013. This makes sense. It's horizontal here, so it's really just going to be this number times this difference. It's really kind of like the P of t times delta t thing, right? But then this one is going to be a little bit more unpleasant. Oh my God, why did I do this? 384t plus 0.036 dt. But I mean, one thing is we should get a number between 0 and 1, and it should kind of go with our original data to some extent. So this one's easy. 0.013t from 55 to 60, right? Oh, so t becomes 1/2 t squared here. Let's just do it. We'll just push through and do it. I just want to see what the answer is. So this is going to be 1/2 t squared. Half of this is 192. So negative 0.000192 t squared. I just change this t to 1/2 t squared, and then the half times this number I think half of 384 is 192 plus 0.036 t from 60 to 65. I'm definitely not going to do all this by hand like I was doing with the stupid gravity problem. Because we'll have to put this in a calculator basically, right? So, but this piece at least is just 0.013 times 60 minus 55, which is 5. And then plus, oh my God, okay. I don't know, ask a calculator. So, negative 0.000192 65 squared. Wait, this, yeah, plus 0.036 times 65 minus negative 0.000192 times 60 squared of 0.036 times 60, right? I'm just plugging in the endpoints and subtracting. Nobody's calculating. Want me to do it? And I say everything's a setup, but now today I seem to be actually doing numbers. So, okay. Nobody's helping me out with their calculator. Negative 0.000192 times 65 squared minus 60 squared. That's that number. Plus 0.036 times 65 minus 60. Wow, she worked out to be nice. 0.06. I think if I did that right, you guys can check me. But I basically just did the 65 squared minus 60 squared times this number with a negative sign plus 0.36 times 65 minus 60. The distributive law for the win. I typed it in correctly, but okay, so that's 0.06. This is 0.065. 13 times 5 is 65. So, okay. I know calculators Calculators are good, but let's just see what our final estimate of the population between 55 and 65 based on this model of this data. So 0.065 plus 0.06 is 0.125. So that's 12.5%. Okay. Just numbers. I mean, make computers do the numbers, but that's the idea, right? Is that fair? Any questions about any of that? All right, I might say a couple words about CDFs just before we run out of time, maybe without writing anything. So find my mouse. Almost done. Okay, so let's see, there's a picture of this. Yeah, there's something, I'll just mention there's some, just to get the idea in your head, and we'll go over this again next Wednesday, but there's something called a cumulative distribution function, which is basically the percentage of the data less than an amount. Right, so you sort of add up the data as you go. So like the best thing I can show you is this picture right here, because this is the PDF that we had, right? But then if you just want like the fraction of the population that's less than 60 degrees, or 60 degrees, 60 years old, or, you know, fraction of population less than 5 years old would be something small, right? Less than 10 years old would be more, less than 15 years old would be more. And you'd be adding, you'd basically be increasing from zero. You'd have zero the population less than 0 years old. When you get to 100 years old, you have one whole fraction of the population is less than 100 years old, right? And you can sort of think about just asking for each X, what's the total percentage of the population less than X years old in the data set? And so you could actually plot that, and we could talk about how to do that, but you actually get a function that starts at 0 and then goes up towards 1, because you're sort of accumulating the total, all the data underneath a certain amount. That makes sense. Like, so the farthest to the left, it's going to be 0 because there's no data less than that. And then the farthest to the right is going to be 1 because all the data is less than a certain range. And so there's, you can kind of convert a PDF into a CDF by sort of thinking about, you really can do it with an integral, I'll show you, but you can sort of get a formula for this, which is this accumulation. It's the cumulative distribution. Even the word function, I can't remember. It's CDF, but it's, oh yeah. Okay, so we'll talk about that more, but then this has properties, and then we'll talk about how you compute median and mean. That's kind of the big part of the last section of the chapter. We'll do that after the break. So I will see you all in 166 and a half hours. Are there 168 hours in a week? There you go. Have a great break. Enjoy Squid Game. Yeah. And the homework for tomorrow night is, you know, you can go see Sarah tomorrow night, last minute if you need to. And Evan did most of the problems. You can bother him. Bye. Yeah, take care. Bye. Have a good break. Lexi, good luck on your test. What test is it? I'm sorry. Oh, you'll kick its ass. You'll kick its ass. Yeah, take care, Evan. Bye, Julia. Have a good break.